In recent years, an increasing amount of research has targeted eye tracking technology and the question of how to use commodity hardware such as webcams to track a user's gaze. But what can we do with the gaze data once we have it? One of the many possibilities is to detect user preferences for objects on a user interface. Why is this relevant? We have probably all made the experience of cluttered user interfaces that present so much information that it is nearly impossible to find the one thing that we are actually looking for. The logical solution is to simply present only the information that is really relevant to the user. The only problem is, how can the interface know what is relevant? On personal devices, it is quite simple to track the user's interactions over time and create user profiles about their preferences, etc. But on public terminals, for example, that are used by many different people with different preferences, this is not possible. And even on personal devices, you might be interested in beef burgers today, but fancy a chicken burger tomorrow. So our perception of what is relevant changes constantly. The idea now is to use eye tracking to predict what is relevant to one specific user at one specific moment. But in order to make predictions, we first have to process the gaze data. This requires two steps. First, we have to extract the gaze features, and second, we have to feed these features into the actual prediction algorithm. Previous work in the area can be roughly categorized along two dimensions. The first dimension is concerned about whether object relevance is predicted for dynamic or for static elements. The second dimension specifies whether only the relevance of an object is predicted, so is the object relevant or not, or whether preferences for one out of multiple objects is predicted. Relevance for static objects has been investigated for both objects in the real world, which are recorded through data classes, and for website elements. Research on preferences for static objects has investigated both text documents and images, usually in the context of search engines. Looking at dynamic objects, that is videos, early work is mainly concerned with detecting object relevance. But later work has also been done on predicting the preference for one out of multiple objects. But what is striking is that, to the best of our knowledge, all the evaluations of previous work are based on a fixed gaze feature and one seemingly randomly chosen prediction algorithm. We could not find any systematic evaluation that investigates whether there are some universal gaze features in conjunction with a specific algorithm that outperform all other feature algorithm configurations. In order to fill this void, we conducted two large-scale user studies in which we first identified a standard set of gaze features and then evaluated the performance of different prediction algorithms with a subset of these features. In the first study, we used a high-quality Tobii Pro X3 120 eye tracker to collect the gaze data of 101 participants. Each participant was shown 3 videos. The first shows 2 instruments that are slowly turning. The second video features 2 musicians playing chamber music. And in the third video, the musicians take turns in describing their instruments. After watching each video, we asked participants which of the 2 elements, so either one of the 2 persons or one of the 2 instruments, they would like to learn more about. In the data analysis, we first wanted to reduce the gaze features to a robust standard feature set. Since we were interested in features that have a high information content for any kind of video, we did our calculations with the aggregated data from all videos. In a first step, we eliminated all features that had a correlation with another feature larger than 0.8. This reduced the initial feature set by 4 features. Then we eliminated 4 more features that showed only a very weak correlation with the participant's true reported preference. This left us with a final set of 9 gaze features. In a second evaluation, we cross-checked whether the extracted features can really predict preferences. We used simple majority voting, so we calculated the gaze features that were recorded for the screen coordinates of one of the two elements, and then we predicted that the element with the highest feature value was the preferred one. The prediction accuracy ranged from 42 to 72%. Across all videos, all features were better than the random baseline of 50%, so we did not exclude any further features from the set. The overall best predictions resulted from the total number of accumulated gaze points, which, for simplicity, we will call from now on gaze count. But for some videos, the average duration of continuous gaze allocation to an element of interest actually resulted in a higher accuracy. So there is no one best feature for all videos. Since the prediction accuracy with majority voting is not that high yet, we conducted a second study to evaluate different algorithms and see whether we could improve the prediction performance. We used the same eye tracker as in the first study and collected the gaze data of 123 participants. This time, the experiment consisted of 5 videos. They were between 18 and 53 seconds long, and 2 of them had 4 elements of interest. The other 3 videos had only 2 elements of interest. As elements of interest, we either showed 2 different video streams in parallel, or we had only one video stream but with multiple objects in it. For each video, we had one generic introduction sequence where all elements of interest were visible at the same time, and additionally, we created one continuation for each element of interest. To illustrate the study procedure, I will use the example of one of our videos, which shows 4 different sports events. First, we showed the participants the introductory scene, during which we recorded their gaze data. In this video, we showed 4 parallel video streams of the sports events. The video paused right in the middle of the scene, and participants were asked to click the stream that they wanted to continue watching. If a participant selected the biathlon event, the biathlon stream would continue, but if, on the other hand, they chose the basketball event, then the basketball game resumed. After they had watched all videos, we asked the participants to additionally indicate for each video how strongly they had been interested in watching each of the elements of interest. Like in the first study, we got the best predictions with the gaze count. But again, this was not the case for all videos. In the first video, the longest fixation was actually the best indicator for preferences. Since the performance varies largely between the videos, we suspected that visual attention is to some degree influenced by some design parameters of the video, such as color, movement, etc. In attention psychology, this effect is called bottom-up attention, and it means that our attention to an object is not directed by our interest in this object, but by salient properties that inevitably draw our attention. We therefore calculated the relative gaze features, which take into account the gaze distribution and true preferences from the entire sample. So if an element receives a lot of gaze points, but most participants don't report it as their preferred element, it has a lower weight. This now allows us to determine when an element attracted a lot of attention only because of salient aspects and not because the viewer prefers it. Looking at our best performing feature, the gaze count, we found a significant performance improvement over absolute features for 2 out of the videos. So we concluded that accounting for salient aspects in the video material does improve predictions. In the next step, we applied machine learning classifiers to see whether the predictions can be further improved by using feature vectors instead of a single gaze feature. Since visual bias can only be accounted for if we train the classifiers for each video individually, we performed best subset selection for each classifier on each video. The prediction performance was quite promising. The best classifier was the multi-layer perceptron with an accuracy ranging from 70 to 82% in the binary classification and from 53 to 68% in the case of 4 objects. This was an improvement over all previous analyses, so including multiple features does have a positive effect on the predictions. Since predictions with relative gaze features and machine learning were significantly better in some videos, we suspected that in these videos, the gaze must be influenced by bottom-up attention. For each video, we therefore calculated the difference between the objects with regard to color, size, motion, texture, detail, and also preference strength. Since preference strength is not an objective measure that can be derived directly from the video, we set up an online study where we showed the participants the same videos and asked them how much they were interested in each of their elements. We define visual bias as the difference between the accuracy achieved with absolute gaze count and the accuracy with multilayer perceptron. We did not find any trend for the intrinsic properties of the videos, but there were indications that the stronger the viewer's preference for an element, the lower the bias. So there does seem to be a visual bias in the video, which is not captured by the 5 intrinsic measures that we tested, but if preferences are strong, the salient factors do not significantly impact gaze allocation. During our evaluations, we noticed that in many cases, the gaze allocation not only matched the participants' selection of the preferred element, but also the ranking of these preferences. We therefore wanted to test whether we can predict not only which element is preferred, but also how strong the preference for each element is. Conducting a multiple regression analysis, we found that in 4 videos, the gaze count explains a significant part of the variance in preferences. We have not yet evaluated different algorithms for predicting preference strength, but the results here show that this is certainly a research direction that should be further pursued. Summarizing our findings, we defined a standard set of 9 gaze features that promise robust predictions for preferences about dynamic objects. So far, we did not include smooth pursuit features, which we suspect could be beneficial for the predictions. We then found that applied individually, the prediction performance of the features depends on the video, but we also found that accumulated gaze points on an element are overall the best individual predictor. We further found evidence that visually salient factors influence gaze allocation and that machine learning classifiers deliver better predictions by, on the one hand, using multiple features, and, on the other hand, accounting for the baseline gaze allocation for a video. We are quite confident that the visual bias does not stem from color, motion, texture, detail, or size of the elements, but we still have to conduct further tests to detect the true causes for the visual bias. We can already say, however, that the visual bias decreases if preferences are strong. A preliminary evaluation showed that it is also possible to predict the strength of preferences. But finding the ideal feature vector and algorithm for these kinds of prediction is something that we have left open for future studies. But already our findings are very encouraging because they allow us to determine which element on a user interface is really relevant to a user. If we remove all the irrelevant elements, we can design more targeted and more effective user interfaces.